checking for cavity for engines and this way.
All right, guys, I'm going to catch up to you a little bit. There's the proof that first derivative. But really understand what I'm saying. I'm going to give this to you on the test. Even if you can't make it work, let go of that. Take this, do the rest of it. So you don't have to get stuck at just the derivative. So many parts to this thing. So critical numbers hopefully are obviously 0, 1, and negative 1. Now I was really nice here. So what do I look at to create this? Well, I look at the freaking first derivative because that's the first derivative test. But just instead of memorizing that shit, why does it make sense? What am I trying to determine right now? Intervals where it's increasing. Okay, what tells me increasing, decreasing? Positive, negative. When what's positive, negative? Not the function. The slope, so the first derivative. So I'm going to hit the pluses and minuses from the first derivative function, because that's what's going to tell me what the slope is, which is dealing with increasing, decreasing. So you have to plug in a point from every region if you don't understand multiplicity. But if you understand multiplicity, this is even. It's going to stay the same sign on both sides of 0, because that's what a parabola does. It turns. It's going to go through 1 and negative 1. So that's what a line does. That's what multiplicity does for me. So if I put in 18 million, or if I put in 2, I get positive, negative, positive. That's negative. It changes sign at 1, stays the same sign around 0, changes sign around negative 1. Or you plug in something from each region if you don't understand multiplicity. Feel bad for you if you don't. It takes a few more seconds, but does everybody see that? So that's why I can now say where it's increasing, because these are from the first derivative, which tells me the slope, which tells me increasing, decreasing. So where's it increasing? Negative 1 to, not to 1. You're so wrong. What's it doing at 0? Is it increasing or decreasing at 0? It is flat at 0. I know this is a tiny point, but you've got to stop at 0 and start over at 0 again. What's it doing at 0? It's not increasing or decreasing, but so that better not show up in any answer. What did I do to tell myself that shit? I put a Z there. So it's not increasing or decreasing. Where's it decreasing? And then of course 1 up to infinity there. So where's the min going to be? Oh, get out of there. There. Started doing stuff. So down, up, still up, and then down. So what's true at negative 1? That's going to be a min. There's a min at negative 1, what? Now where do I put negative 1? Somebody out there's like, I'll tell you where to put negative 1. Where do you put negative 1? In the function, because I want to know where it is. I want to know what the actual output is. I don't care what the, I know what the slope is there. Why would I go and plug it? I'm like, I already know what the slope is there. So when you put a negative 1 in, you get, when you put a negative 1 in, you get negative 5 plus 3, negative 2. And then the max is going to be at 1, yeah, 2. All right, how are we doing so far? Good? Yeah, I like it. So this is what I mean by don't just memorize everything. See why it makes sense, and then it's not memorization, it's just doing what makes sense. Yes? Yes, this is pretty much exactly the way I ask you a problem on a test or a quiz. Exactly like this. I could just say, graph it, doing all the calculus shit, but I try to step you through it a little bit. Alright, so this guy, when I go to do this, how many f primes do I have? All these, which one am I going to use? This one, should yeah. So if I take the derivative, I get 30x minus 60x cubed. I like it. Big ass. Check. I like it. And I love when calculus students are like, look at an ugly number. 20. Nobody did that. Thankfully, but I'm sure somebody did. So when you get the critical numbers, I'll do this one. 0. What do you get from this guy? Yeah, plus or minus root of 1 over 2, or 1 over rad 2, doesn't matter. Rad 2 over 2 if you want to really take it all. When you go to graph this, you can round it to 1 decimal place, right? I mean, when you graph this shit, you're not going to be able to discern between 0.7 and 0.71. If you are, show me. I want to see that shit. So those are my critical numbers for the second derivative. So those are possible locations of what? No, they are zeros. But they are possible locations of inflection points. So inflection points are to the second derivative like maxes and mins are to the first derivative. Where does a max or a min occur? Where the first derivative changes sign. Where does an inflection point occur? Where the second derivative changes sign. Where the concavity changes. That's an inflection point. Does the concavity have to change? No, we did that one. The little cuspy dude wasn't an inflection point because the concavity stayed down. Cuspy dude, you like? Alright, so here's my little sign diagram. I got my gross numbers, poor little numbers. But I know now everybody go, what's the multiplicities associated with what's the multiplicities associated with each of those roots? Even or odd? Okay. I don't want to not use multiplicities, I'm just going to tell you. Could you factor this? You totally could. Now I know that it's rad 1 over 2. So if you did factor it, it'd be a bunch of x stuff, right? So everything is a first power. They're all odd, so it's going to change signs everywhere. Because I don't want to figure out what's between these two. I could. I really hope I don't have to. So what's above rad 1 over 2? I don't know, 3. So if I put a 3 in here, what kind of thing do I get? Negative. So what's this going to be? Positive. Negative. Because they're all multiplicity 1. They're all odd multiplicity. I only have to deal with one input. That's awesome. If you don't understand multiplicity, you got to deal with inputting something from everything. Oh my God. What did I use to create that? Which function did I use? Which second derivative? Because this is a sign diagram for the second derivative. It makes sense. I love it. So what's true back here? What's this mean? Step up. Come down. Come up. I like it. Come down. I like it. Happy to say it. Happy to say it. Whatever you want to do. Negative. So he's sad. Positive. So he's happy. Alright, I'll stop. So so intervals, just really quickly, it's up from negative infinity to negative rad 1 over 2, and from 0 to 1 over rad 2, and then whatever way you want to write that. Down, of course, is from negative 1 over rad 2 to 0, and rad 1 over 2 to infinity. How many inflection points are there? How many inflection points? How many places does the sign of the concavity change? 3. 1, bam. 2, bam. 3. They're all inflection points. Oh shit. So let's list all the inflection points. So I'll do this one. 0, 0. What's another inflection point? -1 rad 2, comma what? What do you get when you plug that in? In fact, let's just start being more realistic here. 1 divided by rad 2 is 0.7, roughly. If you don't believe me, do it. What's rad 2? You guys should know. What's square root of 2? You guys don't know? Look, some of you guys look at me like, what the shit are you talking? Come on, somebody knows what square root of 2 is. You guys have worked with it enough. 1.414, or 1.4, right? So what's that divided by 2? 0.7. Because 1 over rad 2 is rad 2 over 2, which is 0.7 roughly. In human terms, right? I'm going to graph this thing. I'm not going to say 0.7 over 7. No, I'm not going to make that precise. So let's do this. 0.7 comma. Now plug rad 1 over 2. Has anybody done that yet? Plug it into the function. Negative 1.2?
Well, it's 1.23.
1.23? Alright, so 1.2 for human. And then negative 0.7, what do you get when you put negative 1 over rad 2 in? Negative 1.2? Maybe. Let's see. Let's double check. Where am I plugging these things, by the way? You know, like, in the original. I like it. So if I do 5 times, in fact, let me do this for myself. 1 divided by rad 2. Now watch this. Store that in x. So what is 5 times that cubed minus 3 times that 2 that? Yeah, 1.2. I like it. And then if I do negative 1 divided by rad 2, store that next. Negative 1.2, oh gosh. I just didn't believe in it. Such a crazy. Yeah, what am I trying to find right now? What are those, the inflection points? Not the maximum. So I'm trying to find what the function is doing at those x values. So if I want to know the function is doing, where do I plug it? Into the function, f of x. I don't care what the concavity is. I know what the concavity is. I know what the slope is. I just don't know what the function is doing there. Okay. So part of this, when you go to graph this stuff, is choosing a scale that is nice for you. Right? Look at my outputs for my max and min. Goes up to -2 and 2. Right? And this guy is like 1.2, negative 1.2. Maybe I want to make this 1, 2, like that. But gosh. Do you guys understand? You can make the scale, as long as it's consistent on each axis, you can make it whatever makes it easy. If my outputs were 8,000, I'm not going to use a scale of 10. I'm going to use a scale of 1,000, right? Maybe 2,000. You ought to get used to picking your scale correctly. What about the x-axis? Which scale should that be made? Yeah, maybe the same will work. I like it. So 1, 2. They don't have to be the same, right? Love when you guys come into calculus, you don't know that. Scale can be different. Of course it can. This could be years, and this could be profit. Right? So they don't have to be the same. They just have to be consistent on their own scale. You can't go 1, 2, 7, 9. I like that. So here's how this will really, really be the easiest it could be. I don't mean graphic calculus. I mean collect everything you know. So -1, -2 is the location of what? A min. So I'm going to label it min. So that I know when I get to it, I shouldn't go below it. The max is at 1, 2. I'll label it max. My inflection points are at 0, 0, 0.7, 1.2, so 0.7, 1.2. That's 0.5, Jeff. There you go. A little IP next to that. Get that, anybody? No. Make you like, come to George. Negative 0.7, negative 1.2 is about right there. IP for inflection point. What about, I also asked you to find the intercepts. What's the x-intercepts? How are y'all doing, man? You guys all right? So this, believe it or not, I know when I get here, whatever concavity I'm doing has to change. So that's why I label it IP. So I know if I'm doing a concave down, it better become concave up, right? I label max and min, so I know not to go beyond that, right? So your labels are going to tell you what the shit to do as you get there. That's awesome. What are my intercepts? I just have to factor this thing, right? So I get x equals 0, and x equal to plus or minus square root of 5/3, which is approximately? It's approximate. What is square root of 5 to 5 by 3?
1.3.
Who is it?
1.3.
1.3?
Yeah.
I like it. So 1.3 is about right here. Negative 1.3 is about right here. Let me do it, Jeff. It's 1.5. Block. Okay. There's a lot going on here. So what's it start off? What concavity does it start off with? Positive. And is it increasing or decreasing? Decreasing. That I just started. That just get yourself started, and then as you hit each point, it tells you what the hell to do. So it's positive concavity. So it's concave up, and it's decreasing. So it goes like this. Then I go through this, and what's going to happen at this point? Oh shit! I've messed up already. It's really, really coming down. So here it goes through there. Gotcha. And then what's it supposed to do? So and when it turns here, what is it? It's still concave up. So that's why this scale should have been a little bit different. That's right. Well, what happens right here? Now it's concave down. And then what happens right here? Concave up. And what happens right there? Concave down. Through there. Still concave down. That's some weird shit. Now if you graph it on that same scale, let's try to graph this thing on the same scale. Change the scale to be, what do? We did basically negative 2.5, 2.5, negative 2.5. Oh, get out of this scale. 2.5. There you go. Coolness, man. But there are things that tell me like this. If I see that on your picture, that's something that I would never think of. Even me, I know how to flip a mat. I don't think that it's like this. So if I see that, it's kind of like, did they just carve it? So I don't need it to be perfect. This is by hand. It's not supposed to be perfect, but it's supposed to capture the meaning of the calculus stuff that we did. Does that make sense? See, if you did the calculus stuff wrong, your graph better look wrong. Does that make sense? I love it. People are always like, you want me to do the wrong thing? Yes, I want your interpretation of your work to be on your graph. I don't want your work to be wrong and your graph to be right. That's a miracle, and we all know what that miracle is. Bad invention. Right? But that should tell you, if you see something different, like it's doing this and you got this, then look at your second derivative. It tells you what to look at. And if you can't see what's wrong, graph it wrong. Show me you know how to interpret this kind of concavity. Does that, even if it doesn't make sense, just do that.
Okay.
Yeah, all right, that's plenty. I think that's plenty.
We'll do the other side next time.
I think we'll talk about the next quiz we'll talk about it on Thursday, so it's not going to be Thursday.